Hello folks. The last video talked about electric fields associated with point charges. This video is going to take a look at the electrical potential fields or the voltage fields associated with point charges. And here we are back with the template that we've been using for the last several videos. So if you remember, our setup was we have a field producing charge Q sitting here. We have a secondary charge little q sitting out here that's feeling the disturbance, distance r units away. If we were to go ahead and use the calculus that's required to be able to derive potential energy functions, what we would find is that this force function right here, the Coulomb force function, has a potential energy function that goes along with it that looks like this. How that calculation is done isn't really important. That's not something you need to worry about. What you do need to worry about is the bottom line, which, as I said, is that this is what the potential energy function would look like for a Coulomb force. So holding true to form, now we're going to take a look at our charge, our field producing charge, and we're going to ask ourselves what's going on out in space around it. So I'm identifying a point out in space, r units away. There's nothing there, it's just empty space. And we're going to say to ourselves, if we were to put a point charge there and register how much energy, how much potential energy that point charge had at that point, which I might add is identified right by this function right here. This is the amount of potential energy that the charge little q would have if placed in the field generated by big Q. We're going to take that function and we're going to divide by the size of the little charge that's feeling the effect, which is to say we're going to plink off that Q. And what's going to be left over is going to be the voltage function for our point charge. And that is going to end up simply being KQ over R, where the Q involved is the field producing charge, and R is the distance out to the point of interest. That means, once again, that we can rewrite the left-hand side here as the potential energy equals QV. Here's the Q, here's the V. And just to trumpet the final presentation of our overall information, all of this information that we have, electric field generic, electrical potential generic, electric field, electric force, and electrical potential for a point charge, all in one great fell swoop. I'm animating the title, The Generic World, in vivid red. So now it's time for an example problem. We've got a point charge, minus Q, sitting at the origin. We want to know what the absolute electrical potential is at y equals minus A. According to our function, that's going to end up equaling K times the field producing charge divided by the distance to the point of interest, or K times minus Q over A. Observation number one, R is the magnitude of the distance between the field producing charge and the point of interest. That means the R in this relationship is going to be A, not minus A. You don't have the sign of the coordinate tag along. You do, on the other hand, have the sign of the field producing charge tag along. The consequence of all of this is that the electrical potential that's generated by a negative charge is itself going to be negative. So given that we know what the electrical potential is at A as a consequence of the field producing charge, the question we might ask is, how much potential energy would a secondary charge have, like for instance minus Q1's worth, if we were to put it at y equal to minus A? Well, we know that the potential energy a charge has in an electrical potential field equals the size of the charge times the size of the electric potential at that point. Charge that's feeling the effect is minus Q1. The electrical potential is minus K times the field producing charge divided by A. Manipulating, we end up with potential energy of K Q1 Q over A. Observation, the sign of the charge that feels the effect tags along. Notice there's a negative sign. And just as an observation, apparently, if you have a negative charge in a field that's produced by a negative charge, the math suggests that you're going to end up with positive potential energy. Seems odd. Let's see if it makes any sense. Potential energy functions are only useful if you're doing work calculations. So let's figure out how much work the field would do if we force the charge to go from minus A to minus 2A. So we're going to go from here to here. This is our relationship between work and changes of potential energy. This is our potential energy function evaluated at point 2. Here's our potential energy function evaluated at point 1. Remember, the R value, the denominator here, is giving you the magnitude of the distance between the field producing charge and the charge that's feeling the effect. That's why the negative sign didn't ride along in this calculation. Also notice these Q values are magnitudes. When we did the derivation to figure out what the potential energy function was, we unembedded the negative sign for Q1, we unembedded the negative sign for Q, making those magnitudes. So this final expression is assuming that Q and Q1 are positive values, and that's what should go in here. To solve this, we need a common denominator. So we'd like to have 2A in the denominator. To do that, we're going to multiply the top and the bottom by 2. And doing the math yields plus KQ, Q over 2A. Does this make sense? Why? Yes, it does. The electric field is upward. If you put a positive test charge here, it would be accelerated toward the negative field producing charge. Negative charges accelerate opposite the direction of electric fields, which is to say it would naturally accelerate downward if you had a negative charge, which is what we're dealing with. As that's the direction we're moving in, you would expect the work that the field would do would be positive, which is exactly what we're seeing here. In short, it would appear that the theory is working just fine. As a minor side point, we could have done this problem using straight voltages and not potential energy functions. Specifically, the work equals minus the charge that's feeling the effect times the change in the voltage between the initial and the final position. And if you follow down with the calculation, the charge that's feeling the effect is minus Q1. The voltage function that we derived is KQ over R, where in the final position R is 2A, and in the initial position it's A. And by doing the manipulation, lo and behold, we come out with the same work quantity. So you now know what the electrical potential function is for a point charge, and you've seen an example or two of how you could actually use that function in a problem. So in closing, in the words of that great orator, Porky Pig, but that's all, folks.